In the last video, we studied what is meant by upper bound and lower bound of a set, or bounded above or bounded below sets, and we have been trying to give some kind of uh, non lesser than approach for every definitions, right? So at the end of this video, you will understand why I did like, or why I went away from the Rudin's approach here and there, and also I stick with the Rudin's approach. So uh, the main intention stayed as it is, and in this video you're going to learn a lot of things, and this video is going to be bigger video. uh, let's start. In this video you are going to study about Supremum. What is meant by Supremum? Up, Least upper bound, least among the upper bounds, and Infimum. Then examples. The examples part is a very important part to understand what we done till now. Okay, least upper bound property. This is the end of this property, end of this all kind of abstractness. We can end here, and then we can directly go for the real numbers after this. And we have small theorem to understand little bit more about the gaps in the rational numbers, and also it is supporting for the example. So here, more than definitions, example part is a very important part. Suppose S is an ordered set, E is a subset of S, not just a subset, it should be, E should be bounded above. Okay, in with respect to set S. Okay, bounded above with respect to set S, which S is a superset here. Suppose there exists an alpha belongs to S. That means there exists an element in S such that first and most that alpha should be an upper bound of E. That means alpha should not be related to any of the element of E. This is according to our context. Okay, when coming to the lesser than or greater than context, alpha should be greater than or maybe equal to every element of E. Okay, this should be greater than or equal to every element of E. Then only we can call alpha as an upper bound. So alpha should be an upper bound here. If there exists an gamma, any element in S, that element is less than alpha, or that element is related to alpha, then gamma, that the new element, should not be, or it is not an upper bound of E. Okay, that should happen. That means what? When coming to the greater or lesser than context, gamma is already less than alpha. Alpha is one of the upper bound. If gamma is less than alpha and gamma is not upper bound, then what happens? Then alpha is going to be least among the upper bound, because there is no lesser number among the upper bounds. So this also indirectly saying that there may be many upper bounds. Okay, there may be many upper bounds, like finitely many or infinitely many, we don't bother. Among them, which is the least one? How to define least one? It is what? Alpha is what? Alpha is the least among the upper bound, so it must be upper bound. So step number 1 says it should be an upper bound of E. Then suppose there is an element less than alpha, it should not be upper bound. Suppose there is an element which is less than alpha but also an upper bound, that means alpha is not the least among the upper bounds. So in order to define that, we have to follow these two steps, or you can bring your own kind of steps. So alpha should be gamma should be related to alpha, and gamma is not an upper bound of E. If gamma is an upper bound of E, gamma is not related to every element of X. That means if gamma is not an upper bound, gamma is related to every element of E in the context of relation. Okay. Then we can call this alpha as the least upper bound of E, or you can call this as a supremum of E, and we can denote this with this symbol also. After knowing about Supremum, it is very easy to connect this with the Infimum. We need an S, an ordered set, and an subset of S which is bounded below with respect to S. Then if suppose there exists an alpha in S with the properties like alpha is a lower bound of E, and if gamma is gamma is not equals to alpha and not related to alpha, you can read this one as gamma is greater than alpha, then gamma is not an lower bound of E. Okay, what we have here in the context of greater or lesser, alpha is a lower bound of E. That means alpha is less than every element of E. Okay, that means what, in the context of relation, alpha is related to E. If there exists a gamma which is greater than alpha, that means if there exists an element which is not related to alpha but also not equals to alpha, then gamma is not an lower bound of E. Gamma is not an lower bound. That means gamma will never be going to related to any of, gamma is not related to any of the element E. This is going to be happen in the case of, or this is how to understand in the case of relation. Coming to the greater or lesser for the second step, if gamma is greater than alpha and gamma should not be a lower bound. What happens if gamma is a lower bound? Then gamma is an lower bound greater than alpha. Then we cannot call alpha as the greatest lower bound of E. So if alpha satisfies these two properties, then we can call alpha as the greatest lower bound of E. Why? Alpha is a lower bound, and if there exists any number greater than alpha, that is not going to be lower bound. So this is the greatest among the lower bound. Okay, so this is also called as a infimum of E, and it is going to be denoted by this symbol. You remember these two sets A and B, set of all rational numbers whose square is less than 2, and a set of all rational, of course, positive rational numbers, set of all positive rational numbers whose square is greater than 2. Both of them are subsets of Q. Now just take the set A and the Q in pair. So our E is A and S is Q here. So let us try to understand the supremum of A. One thing you should notice that every rational number in B are greater than A, and also whatever the rational numbers present which are greater than every element of A are all in B. A does not have greatest element of every element of itself in A itself. Okay, so there is no greatest element in the set A, and we don't have a rational number whose square is equal to 2. Therefore, if there exists a rational number which is greater than every element of A, then it must be in the set A. So what it means, every upper bounds of A are in B. That means B is the set of all upper bounds of A. If supremum of A exists, it must be exist in B. What that supremum? That supremum must be least among the greatest bound. That means B should have least element in it, but B has no least element in it. This is what we studied in the video number 2. So there is no supremum of A is in rational number set. That means we got an example, we got an bounded example, a bounded set which is the subset of Q such that its supremum does not exist in Q. Alright, please note this point. We got a subset whose supremum not exist in the superset. This kind of possibility is there and it is an example, and also you should take this part into account, that A has no supremum in rational number set. Now consider the infimum of B with respect to Q only. Note now you can see that every lower bounds of B are in A. Again, A has no greatest element in it, so there is no infimum of B in rational number set. So what if set A has supremum in the Q, set B has infimum in Q? Then we would have a rational number whose square is equal to 2. Then there will be no gaps. So this is not possible. So what we are telling here is we traveled from the information that there may be some numbers or we require some different numbers to gaps in the numbers. Now with all these build-ups of order, boundedness, lower bounded above, lower bounded below, then infimum, supremum, now we are at a point or where we know the reason why the gaps are there. The reason for the gap is A has no supremum in Q and B has no infimum in Q. That infimum is that new number and we may call it as irrational. Now it's time to call it irrational, but it's not yet very much built, okay, but we can think of like that to understand. So Q is not continuous. Q is not like a straight line. There are gaps in between. That gaps are because of this property that we can find subsets of a Q where supremum or infimum may not be in the Q. Okay, so now we require one more property, that is least upper bound property. We will deal now. Before that, there are two examples. You take a set of all negative rational numbers, only negative rational numbers, and a set of all non-positive rational numbers. Which is the least rational number greater than all the negative rational number? 0. If you take only non-positive rational numbers, then 0 is the supremum and that supremum present in the set. If you take only negative numbers, that 0 is supremum again, but that 0 is not in the set of all rational number, negative rational numbers. So supremum may or may not be in the set. This is also one thing you should note. And also you just take the set of all positive reciprocals. Among the positive reciprocals, which is the greatest reciprocal, 1 by 1. So 1 is the supremum, and so that 1 is present in the set. So uh, these are two examples in 1.9 example section of the Rudin book, along with the AB. So AB set. So that is all about our traveling from finding the gaps to finding reason to the gaps. Now we shall define this least upper bound property. It is very simple. S should be an ordered set here, and E should be the subset of S, and it should not be null set, and E should be bounded above with supremum of E existing S. Then S is said to have least upper bound property. This is the property we are missing in the set of rational numbers. So this is very important property, and we are going to prove our new number system has this property. Otherwise, how it must have gaps, right? So in order to show that it doesn't have gaps like rational numbers, we have to show that our new number system, real number system, should real number system uh, have this least upper bound property. So this is very important, and this is the core of this uh, chapter. We have a theorem also along with that. Suppose S is an ordered set with the least upper bound property. So we know what is meant by least upper bound property. So every subset of E, every subset of S have a supremum in S, and P is a non-empty subset of S, and P is bounded below. This is important here. B is bounded below. Let L be the set of all lower bounds of B. So B is bounded below means the B should have lower bounds, right? So L is a set of all lower bounds of B. Then supremum of L exists. Okay, supremum of L exists. When the supremum of L exists, whenever B is a non-empty subset of S which is bounded below, and S should be a ordered set with least upper bound property, then only this is going to happen. And alpha is that alpha, or that supremum of L is the supremum of B. This is same thing we found in set of rational numbers greater than square whose square is greater than 2, and the set of rational numbers whose square is less than 2. There one's supremum is the another's infimum. So this is the proper theorem which says that if the least upper bound property is satisfied, then we cannot have gaps in between numbers. So we can construct such kind of numbers. So our new number system should have least upper bound property. Let us prove this theorem. Now coming to the proof of this, since B is bounded below, L is not an empty set. There must be some element which is lower bound. Okay, so L is not an empty set, and each element say Y are less than or equals to every element of B. So these things are little clear. Every element of B are upper bounds of L, and L is a subset of S. And also recall that we just said L is not an empty set. So L is not an empty set, L is a subset of S, and every element of B are upper bounds of L. That means L is bounded above. So we have a non-empty set which is bounded above and subset of S, and S is an least upper bound, S is a set with least upper bound property. So what will happen? L has supremum in S, and let us call that supremum as L. So this completes the part 1 of this proof. What we have to prove? We have to prove that alpha is equals to supremum of L exists in S. So there exists a supremum. Let us call this as alpha. If there exists an gamma which is less than alpha, then gamma is not an upper bound of L. So gamma is not in B. This means alpha is less than or equals to every element of B, lower bound of B. If beta is greater than alpha, then beta cannot be in L. I repeat, if beta is greater than alpha, then beta cannot be in L. This means that alpha, which is the supremum of L, is the infimum of B. Why? Alpha is the lower bound of B, but if there exists a beta greater than alpha, then that beta cannot be lower bound. This means alpha is the infimum. So this means alpha is the infimum of B, the same alpha, which is the supremum of L, that will be the infimum of B. So this is how we can prove. This is just to have clarity about why we need supremum, the least upper bound property. Now coming to the greater than or lesser than symbols, or instead of taking them like things like very abstract way, just think a real number, just think about relations instead of a lesser than. Why I insisted like that? Because suppose if you are creating a new number system and if you don't want any gaps in between, and there is no regular or formal way of lesser than or greater than notion, then how can you give an approach? Then you find a relation which has the order, which has the properties of the order what we defined, and then you choose the one of the relation as the least upper bound, lower bound for the lower bounds, and then reverse it for the upper bounds, then go for define carefully about supremum and infimum, and then go for least upper bound property. There you have a new number system which is almost have all the features or very important features of the real number systems. So this will help us to understand how the theorems or how the theories and as well as how the scarcity made to develop new number system. So we traveled from one point that we need more than rational numbers, then we found gaps, and then we went a little bit abstract to find order and all those things. Then we combined everything, and then we showed that because of the least upper bound property, Q has gaps. That means, of course, Q has gaps, then only we created this least upper bound property. Now we have some tool to understand why gaps are present. Okay, so now things getting very easy. Now no need to think about abstract way. Just go for fields and then ordered fields, and then finally our great or our anticipating most anticipating theorem, that is uh, existence theorem. So there we can wind it, uh, and then we can go for Euclidean domains, and just to have some more structures of the real numbers, and then Archimedes theorem, all those things we can learn. But we should know what happening behind this. So that is why I try to give uh, conclusion like this. I went a little bit away from the Rudin's approach, that was to give an explanation uh, how to deal with creating a new number system, and I stick with the Rudin, just to stay with the notion of uh, lesser than or greater than to understand, as well as we are going to define a real number system, and we know real number system, and we will deal with them with the lesser than or greater than symbol soon. So i stick I stick to both, and that is why it took a lot of time.